we're now going to use the graph of a function to find the limit. So here we're given the graph of a parabola, and we're looking for the limit as x approaches 0 of that function. Well, as we approach 0 from both the left-hand side and the right-hand side, the y values are approaching 1, so this limit is 1. Pretty straightforward. It's the value of the function at x equals 0. In the second one here, the value at x equals 0 of our function is undefined, but that doesn't affect the limit. The limit is simply the y value that we are approaching as we get close to x equals 0. So from the left and from the right, it is approaching y equals 1, and this limit is still equal to 1, even though the value of the function is undefined. In this example, from the left-hand side of our function, the limit as we approach 0 is 2. We would notate this as the limit as x approaches 0 from the left of f of x is equal to 2. And from the right-hand side, as we approach x equals 0 from the right, which is notated the limit as x approaches 0 from the right of f of x, it's equal to 1. In order for a two-sided limit, the limit as x approaches 0 of f of x, to exist, the limit from the left and the limit from the right have to be the same. In this case, they are not the same, and so this limit does not exist. If the limit from the left and the limit from the right are the same, then the two-sided limit is also the same. This is an important point that we use when we talk about the definition of continuity. A function is continuous at any number, c, if and only if all three of these conditions are satisfied. The value of the function at f of c has to be defined, the limit as x approaches c has to exist, and that limit has to equal the value of the function. There are three different types of discontinuity that you need to be familiar with for the AP test. They are removable discontinuities. So there are two examples of that here. There is a removed point at x equals c, and here down at the bottom there is also another removed point at x equals c, even though there is a point for the function that the function equals at c. Both of these are still called removable discontinuities. For both of these, the limit as you approach c is the same y value that your function is getting close to. In this one down here, it is not this point. That is not the limit as x approaches c. The limit as x approaches c is whatever the y value at that hole is. This one is called a jump discontinuity because the function is coming along, it stops, and it jumps to another y value at that exact point, similar to the last function we were dealing with. The limit from the left is one thing, the limit from the right is another thing, and the limit here at c does not exist. And the last type of discontinuity that we'll deal with is an infinite discontinuity, which is where the function is approaching a vertical asymptote. Those should be pretty easy to identify. What we'll do here is we will find the values of a to show that f is continuous for all real numbers. So we'll have to use the definition of continuity for this. This is a very common problem type on the AP test. So the first thing we need to do to show that something is continuous at a point, and the point we're interested in here is x equals -1, is we need to show that the function exists at x equals -1. So, yes, at -1 the function is equal to a times -1 plus 5. We also need to find the limit as x approaches -1. Well, the limit as x approaches -1 can be found by using the top piece, because these are the values of the function, x cubed plus 3x squared plus 3x plus 1, that we get when we are approaching -1. So we look for the limit as x approaches -1 of x cubed plus 3x squared plus 3x plus 1 over x plus 1. If you plug in -1 to this, you end up with -1 plus 3 minus 3 plus 1, which is 0 over negative 1 plus 1, which is also 0. So this is an indeterminate limit. With an indeterminate limit, we have two ways of evaluating it. We can either factor the top. This factors into x plus 1 cubed, and then we can cancel, or we can use L'Hopital's rule. So if we use L'Hopital's rule here, we end up with the limit as x approaches negative 1 of 3x squared plus 6x plus 3 over 1. Now when we plug in negative 1, we end up with 3 minus 6 plus 3 over 1, which is 0. So the limit as x approaches negative 1 exists. It's 0. The value of the function at negative 1 exists. It is negative a plus 5. And for the function to be continuous at negative 1, we just need to set the value of the function equal to the limit. So negative a plus 5 equals 0 indicates that negative a equals negative 5, or that a is equal to 5. So if this was 5x plus 5 when x was negative 1, we'd have a continuous function for all real numbers. Another important piece of continuity is the intermediate value theorem. The intermediate value theorem says that if you have a function that is continuous on a closed interval from a to b, then any number between f of a and f of b, for example, w, can be found by choosing a number, c, we'll call it, between a and b. So if it's a continuous function, every value between f of a and f of b can be obtained by choosing a value between a and b. That's the intermediate value theorem. One of the most important consequences of that is that if f of a is negative and f of b is positive, or vice versa, if there's a sign change between f of a and f of b, it means that it must have crossed through the x-axis in some place. Because this function was continuous, there must be a 0 or a root somewhere on the interval from a to b.